Good morning, everybody. I'm sorry I could not come and be with you today because I'm going to be watching Alice today. Her daycare is closed for religious reasons. So we're going to today do applications of exponential functions. And the first example we would do if I were here, and I'd have you kind of brainstorm about it. So let's say we have like a hypothetical city like Charlotte, North Carolina. And it has 687,000 people, 2008. And you want to find what the population is going to be next year if there's a 3% growth rate. So what you would do is take 3% of 687,000. And you could go to your calculator and do 0.03 times 687,000. You get 20,610. And you add that to 687,000. It's really important when you're doing percentage rates that you do them in the decimal form for these. And then we do the same thing going from 2009 to 2010. So we put, so then what we would do is we would kind of look at, so we get 21,229. And we add that to 707,610 to get 728,839. And if it asks you, what's the ratio between 2009 and 2008, you divide the population by 2009 by the population in 2008 and get 1.03. So what's happening every year is that everybody who, population that was there before, you're going to have that same number plus 3%. So 100 plus 3% is 1.03. And the ratios are going to be the same if you do the same exercise again. So the point of an exponential function is rather than increasing at a constant average rate, you're going to be increasing at a constant percentage rate for the situation. Now, the two equations that you're going to be given, you're going to be given one equation for exponential growth, and then you're going to be given another equation for exponential decay. Now, the A represents the initial amount. So what did you start out with? The R represents the percentage rate that you need to be putting as a decimal point. So, 2% would be 0.02, 10% would be 0.1 or 0.10, and then time is going to be t. So we could actually write an exponential function for the situation of Charlotte, North Carolina. So we would say that that's 687,000. Population's growing, so we're choosing the 1 plus 0.03 to the t. And we get 1.03 to the t times 687,000. So if it asks me, like 9 years down the road, this was last done in 2017, so if it asks me what the population is going to be after 9 years, you plug in the 9 into the formula and you would see what the approximate population would be. This part over here, how long will it take for population to double? That's just to get you thinking a little bit more. For example 2, this is a exponential decay problem because of the keyword of remove. So when we do that, it's saying that it's going down by 20% per year of the pollutant. So you're starting with 18 micrograms of pollutant per liter. And you're going down by 20%. So 1 minus 0.2, it's going to be 0.8. And you're going to do 0.8 to the t times 18, which is our initial amount of pollutant. So if I want to know what the pollutant is going to be after 5 treatments, I can plug in the 5. And remember, do the exponents before the multiplication, and you get 5.898. Another example that I like is buying a new car. So when you buy a new car, it's not the best investment because it appreciates, goes down in value. So let's say you buy like a Toyota Corolla or a Honda Civic that's $20,000. So that's what we start with. And it goes down in value by 15% per year. So you're going to choose the minus equation because it's the exponential decay. So we do 1 minus 0.15, and we get 0.85 to the t. And then, after that, we multiply that by 20,000, and that is going to be our equation. Now, let's say we want to know, what the value is going to be after 5 years when you pay your loan off. You actually go and you plug in 5 into the 0.85, and you exponentiate it, multiply it by 20,000, and get 8874. Another formula that you will be given is the compound interest formula. So this is a little different because you still have the principal. So that's the amount of the loan, or what you invest, put interest. The R is going to be your annual rate. And then the N is the number of times per year that you're compounding the interest. And so that's what the N is. And then you're going to put, for your T, the number of years. And then the A is going to be how much you would get. So let's say that you decide to invest $100 at 4% quarterly. So that means that 4 times per year. So when I set up this calculation, I start with the principal. So that's the amount that I invest, or the amount of loan that I'm going to be taking out. And I plug in 100. And then my rate is 4%, so that's 0.04. And my N is 4 because it's compounded quarterly. And the time is going to be 5 years. So it'll be about 100 times 1 plus 0.04 over 4. And remember, do the parentheses first, order of operations. So it's going to be 1.01 to the 20th, which is 4 times 5. And it would be $122.02. So you get, $22.02 after 5 years at a 4% take of $100. So you could get like a free steak dinner at a restaurant or something like that. Let's say that maybe you do $10,000 instead. And we have a 6.5% interest rate. So the 6.5% interest rate would be 0.065. So you're going to plug in 0.065 for your R, and we'll just say that it's compounded annually, so once a year. And let's say we want to know how much we would get at the end of the first year. So at the end of the first year, we would have 1.065 to the 1. And we'd actually get $10,650. So you'd actually earn $650. Example 6 is actually a very relevant example. So you have 2 choices. You got to think about your retirement package. So either you could be paid lump sum of $20,000 for each year you work for the company, or the company will deposit $10,000 into an account that will pay 12% annual interest rate. So we're going to write an equation that represents each option. So if you get $20,000 a year in retirement monies, that's going to be 20,000 times T. Just a nice straightforward linear function because you are guaranteed that $20,000. And then for option 2, we start at 10,000, we put that in, and then we do 1 plus 0.12. It's compounded monthly, so 12 times a year. So we're going to divide by 12. So we have 1.01 to the 12t. So let's say we want to retire, start work at 25 years old, and you want to retire at 65 years old. So if you get to $20,000 a year, even though initially it would be better because you get that $20,000 instead of $10,000 and you get it every year, you multiply that by 40 and you get $800,000. Versus for option 2, you multiply by 1.01 and then you do 12 times 40 for your exponent. And you get 1.1, a little bit over 1.1 million for that. And that completes the general overview of the notes of skill 16. What I'd like you to do today is I would like you to try, get the filled in notes. So you want to be able to fill the notes in so that you can have those examples to work out. And then after that, I want you to try the IP. So there's some relevant example problems that you are going to be using. It is extremely important that you are using the formulas that are given to you. These formulas will be provided on the test, but you are expected to be able to use them. So I expect that you're able to read through and say the situation and growth or decay formula, choose the right formula, come up with a custom formula, and then plug in the information that is needed. Please feel free to email me if you have any questions. Alice will probably have some nap times, and I'd be happy to answer emails over the weekend too. And I hope that you have a very productive day.